Right, today we'll be talking about how we are going to manipulate quadratics and some of the more advanced techniques that we use in doing this. Now, we can go back to basic simultaneous equations. So something like y equals x squared and y plus x is equal to 6. Right. Now, we can tell from here that this on the left here is a curve because it's an x squared, and we can tell that this on the right is a straight line. So what we're looking at here is the intersection of these two lines, right? So when we're doing this, the first step is obviously to put into the same terms. So y equals x squared, y also equals 6 minus x. So x squared is equal to 6 minus x. And you can tell from here that this is a simple quadratic equation, which simplifies to x squared plus x minus 6 is equal to 0. And then from there, you'll get your roots of x plus 3 and x minus 2. Right, and then that goes into the obviously equal to 0, so then it's going to be x is equal to negative 3 or x is equal to 2. And those are your roots for that basic simultaneous equation. So that is the point of intersection between a line and a curve. However, they do get somewhat more complicated, right, when we start adding in more terms. For example, let's take the equations x squared minus 2xy, right, plus 3y squared is equal to 6, and the equation 2x minus 3y equal to 3. Now, doing this way is going to take a long time if you're simply going to make them equal to each other and solve them. It's going to take you a while, and it's going to involve fractions and that sort of thing. So the best way to do this is to substitute, right? Right, and to do this, what we're going to do is we're going to substitute in for 4x squared. Now, why are we doing this? Well, because it makes sense to. So we've got 2x is equal to 3y plus 3, right? And to get this into 4x squared form, we're going to simply square both sides. So it's going to be 4x squared is equal to 3y plus 3 squared, right? And this squares out to obviously 9y squared plus 18y plus 9, right? So now we've got this nice expression for 4x squared on this side. And we're going to take the original equation and we are going to convert that into 4x squared as well. So the original equation was x squared minus 2xy plus 3y squared is equal to 6. Obviously, to convert this to 4x squared, you simply multiply the whole equation by 4. So 4x squared minus 8xy plus 12y squared is equal to 24. Now, here comes the substitution. Instead of making all of this equal to 0 on one side and doing the same for the other equation, what we're going to do is we're going to substitute directly in for 4x squared. So remember the equation we had earlier for 4x squared, which was 9y squared plus 18y plus 9, right? And now this is going to be minus 8xy, right? But instead of working with 8xy, because we never work with xy, we can substitute in for x. And the expression we had earlier was 2x is equal to 3y plus 3, right? So what we can do is just take out the 2 from this. So it would be minus 4, right? 4y. And substitute this in 3y plus 3. Okay, and then we just add the last term here, which is plus 12y squared is equal to 24, right? And what we've really done is we've made smaller substitutions than we would normally. What we've done is we've replaced the x squared, 4x squared, with another one, and we've replaced x. So we've removed x from this equation, leaving only in terms of y, right? And all of this boils down and resolves out to 9y squared plus 18y, oh sorry, my bad, plus 6y minus 15 is equal to 0. Right? And you can see this is an easy quadratic. From here, it goes down and it reduces into 3y squared plus 6y, plus 2y minus 5 is equal to 0. Right? And this is a simple quadratic. You can punch this into the quadratic formula and you'll find the y coordinates. And then from there you can find the x coordinates of the original equations by punching them back in. Remember to always leave your x and y coordinates grouped together, so it would be like x equals 1, and then you comma y equals 5, and then on the other side you'll add x equals 2, y equals 7. It's not the answers for this equation, but it's just random numbers, but you group them together, right? Otherwise the answer is going to be incorrect. Okay. And from there, we can come to a few more questions that they're going to ask you. Things like, how many points on a line are there? Right. So at how many points does a line meet a curve? So we're going to do an example here of x plus 2y equals 3. And this is our line. And we're going to go and add our curve in, which is 2x squared plus y squared is equal to 4. Right? And obviously we can just sub in for this. Right? And to do this, we're going to do x squared. Okay, so 2x, for this one here, let's just simplify this quickly. So 2x squared is equal to 4 minus y squared, right? And then we're going to put this into the same format, which is going to be 2x squared is equal to 3 plus 2y, right? Oh, sorry, 3 minus 2y squared. 2, 3 minus 2y squared, right? So we can obviously put these together. Which becomes, we've expanded out the 3 minus 2y squared to become 4y squared minus 12y plus 9, right? And then on the other side, we've got this equal to 4 minus y squared, right? And then that simplifies down to 9y squared minus 24y plus 14 equal to 0. Right? And from here, they've asked us, remember, at how many points does the line meet the curve? So what equation do we have that fits that super well? Well, we've got the discriminant, right? So b squared minus 4ac, right? And the result of this simply would be some negative 24 squared minus 4 and 9 times 14. And you can see this is going to be a positive number, right? Equal to 0. And when it's a positive number, it means there's two roots. So it means that this line meets the curve at 2 points. Okay. Now we're going to go into some more advanced substitution, which can kind of feel like cheating at times because it is. And you've got to be careful with it, but it does lead you to be able to solve some rather annoying equations. So we're going to take an example of a quartic equation, right? We're going to take t to the power 4 minus 13t squared plus 36, and let that be equal to 0. Now, ordinarily, we can't solve this because it's got a to the power 4 in it, which is frustrating. It's not a quadratic. Well, we're trying to reduce this to a quadratic, so how do we do that? What we're simply going to do is say that t squared, and we're going to let that be equal to x, all right? So in turn, what that means is that x squared is equal to t4, and t squared obviously being equal to x. So we can rewrite this. I'm going to just delete this so I can leave that up there. We can rewrite this as x squared minus 13x plus 36 is equal to 0. And from here, this is an easily solvable equation with x minus 4 and x minus 9 equal to 0. So x equals 4 or x equals 9. And you can see we've just substituted in a new value for these things. However, it's not going to work with everything. It needs to be consistent across the board, so it would be a multiple of 4 and multiple of 2, and it's not a common equation to come across. Now, we can do a new stand, in which we would ordinarily not, and we can explain why there's an advantage, right? So we've got root x being equal to 6 minus x. And you can obviously easily square this equation. So what you would do is you would just square both sides, right? So this squared and this squared, so it would just be x equals 6 minus x squared. And you can expand that and you can solve it and everything's fine, right? But because we are squaring it, we're not just finding this, we're also finding x equals negative 6 minus x squared. So what ends up happening is that you need to check your answers once you've got your roots, because sometimes one or two of them won't always satisfy the equation, which means that you have got faulty roots. Now, to get around this, what we're going to do is we're going to substitute in this equation root x for y. Okay, so now from here you can retranslate this as y equals 6 minus y squared, because remember, if this is root x, right, is equal to y, then y squaring both sides would logically make x y squared. Okay, and then this gives you a nice simple quadratic. Y squared plus y minus 6 is equal to 0. So obviously we're going to get y equals 2 and y equals negative 3, right? Okay, now the one thing you've got to be aware of when you're doing this is that because y is equal to a rooted number, which root x in this case, root x cannot equal a negative number, which means that this solution cannot be negative 3, so this is your only actual root. Now this is how you have now solved this equation. So you only have the number y is equal to 2, and substituting this in obviously makes x equal to 4. Right, and this is the only true root. So otherwise it would be, and you remember to give them in the next to each other. So it would be x equal to 4, and then comma y equal 2. And the other one would obviously be y equals negative 3, x equals 9, but because x cannot be negative 3, it doesn't solve, right? Now, what we can do is we're going to try and find some tangents. And we're going to see if a line is a tangent or not to a quadratic curve. And at a tangent, right, the discriminant for both of those lines is always going to be equal to 0. So b squared minus 4ac will be equal to 0 because tangents always have one root, one repeated root, right? And so at the tangent, the b squared minus 4ac will always be equal to 0. So how does that help us? Well, that can help us in a couple of ways. And normally it's to find unknown coefficients. We're going to go and take a look at the coefficient here, which is the line y equals mx plus 1, right? And we're going to say this is a tangent to the curve x squared minus 2y squared is equal to 1. Okay. Now, this mx here is throwing a wrench to things, right? It's 3 variables in an equation that you want to be simultaneous. But it doesn't have to be so complicated. We can simply just substitute in here, right, for y. So what this becomes is no. Okay, so we're substituting into this equation, right? X squared minus 2, and then we're substituting in for y, mx plus 1, and we're putting this equal to 1. Right, simple enough. Ah, this is squared, my bad. Okay, and then we're going to expand into this horrible thing, which is going to be 1 minus 2 m squared x squared, right? Because what we've done is taken 1 minus 2 m squared out of this and this, right? Minus 4 m x, because minus 2, that's squared here, minus 3, and put that equal to 0. Right? And now we've got the completed simultaneous equation for those two lines. Now, what do we use it for? Well, we use it with the discriminant. So to put this into b squared minus 4ac form is a bit of a task. It's going to be b squared, which is minus 4m, minus 4a. In this case, a is 1 minus 2 m squared times c to negative 3. Right? And because this discriminant is equal to 0, remember at a tangent, the b squared minus 4ac is equal to 0. We can place it like this. And you can see here we're going to get an expression. Which is simply going to be 16m squared minus 24m squared plus 12, right? That's the expanded form of that, and we can simplify this down to negative 8m squared plus 12 equal to 0. So it would be 8m squared is equal to 12. And from there you can divert that. M is equal to negative 3 over 2, negative or positive root 3 over 2, because we've gone 12 over 8, which is 3 over 2, and we've rooted that, which is squared, and always when you're doing a root, it's plus or minus. So this is the value at m for which there is a tangent to the curve. So for that line, these are the points where that line meets that curve, either at plus or minus root 3 over 2. And this allows us to find the tangent values for lines and curves and meeting them. And this has just been manipulations of equations. Nothing super new or complicated or anything. This is all just basic mathematics and manipulation of the equations, but they are simply clever things that you should keep in your mind when you are exploring the equations and trying to find an answer and trying to find variables that you didn't have before, or perhaps a way in that you couldn't find before.